start again. Good afternoon, everyone. My name is Rez Mani, and I work for company Allied Scientific Pro. And the name of today's webinar is Laser Cleaning Method and Case Studies. I've given this webinar a number of times, and every time I try to include the new activities of the companies, and if there's a new case study, I'll add to the presentation. So it would not be identical to the previous one, and hopefully it won't be repetitive for those who attended multiple times. We roughly have these webinars on laser cleaning every 3 months. So the webinar will be recorded and is being recorded, and the recording will be sent to you soon. We will have a Q&A session at the end. Also, you can feel free to type your questions in the chat box also. In case you have any, I'll answer them at the very end. Uh, the GoToMeeting platform is not really meant for showing videos. So for this reason, you may find some low quality there, but we will send you the link for all the YouTube videos so you can watch them later. So let's move on with the webinar. And this is the outline of the webinar. I'll talk about the laser ablation process, which is a more general case, which may include drilling, basically cutting, scribing, and also laser cleaning. So laser cleaning is a subset of laser ablation. I'm going to go back and forth between the two, laser ablation and laser cleaning. Just keep in mind that laser ablation is a subset of, sorry, laser cleaning is a subset of laser ablation. I'll talk about different types of lasers used in laser ablation. We'll compare it with other competing surface cleaning methods. And we'll then go into a little bit of physics of laser ablation and talk about material properties and laser parameters, how they will affect the laser cleaning process. We would explore different time zones, femtosecond, picosecond, nanosecond regimes. We would see the difference between Galvo and polygon scanners. And then we go into some applications. So you notice I have applications and case studies. The difference is applications is something that exists for the laser cleaning, and we haven't done it, but I've dug out the information from different papers and presentations. But the case studies are the ones that we have actually done ourselves. So here we have applications and case studies. And then we would also look at some of our systems, the 100 watt, 200 watt, 300 watt, and 500 watt laser cleaning systems. So this is the outline of the talk. And so we start with the principle of laser ablation. So the idea is basically to remove coatings and dirt from a surface by focusing a laser beam on the surface. So once you do that, several processes happen. One, there will be a high temperature gradient and a high mechanical stress, and plasma is formed, which causes the formation of a shock wave, and the shock wave blasts the coating from the surface. So this is generally how it happens. Both CW and pulse lasers can be used for laser ablation, but we focus here on this talk mostly on pulse lasers, simply because you have more control over the parameters such as pulse width, repetition rate, pulse energy, and so on. For a CW laser, continuous wave laser, the only parameters you can control is the type of laser, which is determines the wavelength and also the power. So pulse
Sorry,
laser,
Raz, sorry, can you make the presentation full screen?
it is full screen. I'm doing it full screen right now.
Does it show? Anyway, okay.
Let me. Yeah, it is full screen. Right now, it should be full screen.
All right.
Okay.
It is full screen.
Yeah. Thanks, Les. Okay, so let's move on. So here is also more on the laser ablation mechanism. This is from a Malaysian paper, Malaysian authors. They were exploring the application of laser cleaning in automobile industry, and they're showing that there are these paint layers and coatings. The coatings in automotive industry mostly consist of resins, pigments, solvents, and additives, and these are all deposited on the metal substrate. So when one wants to remove them, you would focus the laser beam, and this would be absorbed. The energy would be absorbed by the coating, and a shock wave is formed, and it cracks the network, and then basically blasts all the particles of the coating. So that's how the coating is removed. So this is generally happens when you have shorter pulses and higher energies. Uh, Here also you see there's another diagram that shows this. In some cases, the coating is transparent to the laser beam. So the metal substrate underneath absorbs the laser beam, and then the shock wave is formed there in the metal substrate, and then it blasts the coating at the surface, and that is a different process. It's called spallation. So we'll talk about that when we examine the nuclear power plant contamination and removal. There's also another way of removing when the energies are less and when the pulse widths are larger. You can see that there won't be a shock wave form, but the coating removal is just by thermal ablation. And this is also from the same paper. You can see that laser energy induces a thermal decomposition mechanism, and flames and smokes are emitted from the surface. So these are some different types of lasers used for laser ablation. So some of these are gas lasers, and some of them are solid state lasers. From left, you have the excimer laser, which is a UV wavelength laser. You have anywhere between 126 to 351 range. UV is a gaseous laser. This is more is basically suitable for the lab environment. It's not really meant to be used in the field. It's a low rep rate laser, but it's suitable for germicidal applications, basically, and photodissociation. Then another laser is a CO2 laser. It's a gaseous laser, and it's very popular in the industry for cutting, especially, but it's also used for cleaning, and that's a 10 micron emission. So the medium of emission is a gas, a CO2 gas. And then you have the neodymium YAG laser, a crystal laser at 1064 nanometers. Sorry. So this laser also very much used in laser cleaning, and is compatible to fiber optic, which is a really great advantage. You can also get the multiple of 1064 at 532 and 266 nanometer by putting a harmonic crystal in front of it. And finally, you have the Ti Sapphire laser, which is a tunable solid state laser from 650 to 1100 nanometer. You can tune it by rotating the crystal, but it's kind of expensive, and it has to be powered by an argon laser. It has femtosecond pulses, and basically lower power. So these are some general lasers that are used, but the one that is very special is the fiber laser, and those are also part of our systems. And the fiber laser has many advantages simply because it doesn't use mirrors on either side of the cavity like the normal lasers. In any cavity there are mirrors. Here there are some scribing inside the fiber optic that acts as a diffraction grating and only reflects one wavelength. So once you pump the fiber optic, the radiation goes back and forth and gets amplified and exits the fiber. So this way you have the advantage that the radiation is generated inside the fiber optic, and you can use the flexibility of the fiber optic to move the beam around anywhere you want rather than relying on mirrors. So the laser medium has doping materials such as ytterbium, erbium, or thulium, and the pump light is diode laser. And this laser has some advantages such as high pulse energy, high average power, good beam quality, and variable pulse length. Okay, so now let's look at the laser cleaning, which is a subset of laser ablation. So for this application, you use lasers to remove rust, or paint, or coating, dirt from a surface. So unwanted layers of or contamination from a solid substrate is removed. So in order to get a better understanding, we have a YouTube video to show here. This is actually our 100-watt system. So the box contains all the pumping mechanism. Then there's a fiber optic here. Let me actually activate uh, the laser pointer so I can show better. So this is a fiber optic system, fiber optic cable, an optical isolator, and this is the laser head here, which contains the galvos, and there's also a lens here of a certain focal length. So we can go ahead and uh, activate this YouTube video so you can see what's going on with our laser cleaner. You can see the rust is being cleaned here from a metal pipe, and that's the plasma that is generated, and the vacuum pump is removing all the debris on site. So it's a dry process. It's not contaminating the environment. Okay. Okay, so that was that. And let's move on. So, other applications of laser cleaning technology, it's used in many different industries for conservation and restoration. We have cleaned the Parliament building in Ottawa. We have also cleaned some infrastructure like bridges in Quebec. Uh, Also for automobile, aerospace industry. Can you please mute your microphone? Thank you. Everyone should be muting their microphone. Thank you. So aerospace, you have the aircraft and equipment. We have some videos we'll show you from the Canada Air Aviation Museum, and also ship's body part. We have some uh, case studies in the Halifax shipyard from a ship. In industrial, we have done cleaning in the Caterpillar plant, also in nuclear or radioactive cleaning environments, nuclear plants. We have done some cleaning or demoed the laser cleaner. So these are all different industries that benefit from our laser cleaning process. So, what are the important parameters for laser cleaning? Things that we should consider in the laser before we choose that laser cleaner for our application. One is the wavelength of the laser. So, we have to consider that some wavelengths are heavily absorbed by some material, and some others are reflected by the same material. For example, metals, they reflect mid-infrared wavelengths are around 10 micron, but they heavily absorb the near infrared, which is around 1 micron. But on the other hand, polymers and paint, they absorb mid IR much better than near IR. So one has to consider that. So when you're using the laser to clean paint from a metal surface, if you use the mid IR laser, it's inherently safe because the paint absorbs the mid IR and the metal underneath reflects it, so it cannot damage it. But there are some disadvantages for the mid-IR lasers because they are not compatible with fiber optic. And you can use the same cleaning if you take care of the parameters carefully, if you have the proper recipe with the near IR laser, which is our system. You also have the pulse duration. I'll get into the physics of laser cleaning. Longer pulses, they have more penetration depths and they require more fluence to ablate the material. So you're going deeper into the material. If you're concerned about substrate damage, you shouldn't be using a larger pulse width. Pulse energy, obviously, the rate of ablation will be higher when you use a higher pulse energy. And for the beam shape, smaller beam shapes are usually used for maybe historical monuments where there are a lot of nooks and crannies, or if you have concrete which has pores, you use a smaller beam shape. But if you have a wall that is flat, there are no features like the body of a ship, for example, it's better to use a larger uh, linear beam so that you can do the job faster. And repetition rate affects it. It will increase the depth of ablation because of thermal effects. So for the same pulse energy, if you have higher repetition rate, there's accumulation of heat, and that would reduce the threshold fluence due to heat accumulation. Here are some other parameters that I dug out from some of the papers. A scan speed would basically decrease uh, the depth of removal. You can see here the plot of depth of the crater versus scan speed. So with larger scan speeds, the depth of removal would decrease because the dwell time of the beam on the surface is less. And obviously, number of passes, the more number of passes increases the ablation rate. And also there's a substrate temperature is another parameter that has to be considered. Here is a plot by the author Shamsujoha about removing uh, rust or paint from uh, from a steel surface, stainless steel surface, and you can see that the as long as the fluence stays below uh, 2.3 joules per centimeter square, there is reasonable temperatures here. Like this peak roughly coincides with the melting point of steel, which is 1500 C. And this is actually a Kelvin, so it'll be around 1800 Kelvin. So the temperatures are kept below the melting point of steel for 2.2 and 2.3 joules per centimeter square. But as soon as the fluence goes above that, you can see there's a sharp rise in temperature at 3 and 3.5. The temperature is rising very rapidly, and there's a lot of melting of the substrate. So one has to take that into account when you're doing the laser cleaning, what value of fluence you are using. Here is some comparing other methods of cleaning the surfaces with the laser cleaning. So from left to right, you have mechanical abrasives, chemicals, dry ice, sandblasting, and water jetting are some of the main competitors of laser cleaning. And for mechanical abrasive, you have this rotating disc that could potentially damage the substrate. It removes the paint, but it could also damage the substrate. It would also not good for the environment. The debris will go into the environment. You have the chemical method where you apply a chemical um, a compound on the surface and you wait for a few minutes and then you scratch it. So this could go into areas where you don't want. and also the scratching may damage the surface. And then you have these high pressure nozzle methods, the dry ice, sandblasting, and water jetting, where the operator needs to have heavy personal protection equipment because whatever secondary medium is coming out of the higher pressure nozzle could bounce back from the surface and hit the operator. And there's a big force of reaction there in these nozzles, so the operators nearly has to apply a lot of force to hold the nozzle because of this reaction force that is there. So the one main one is the sandblasting method, which is used in industry a lot. But the problem is that you need to do a lot of preparation before the operation, and you have to do a lot of cleaning after the operation because all the dirt is returned to the environment and a big mess is produced. We had people from the shipping industry complaining about the mess that the sandblasting would make in a shipyard. So these are not good for the environments, make it very dirty. They're very noisy also, and the operators, they require heavy protection equipment. And they all require secondary medium. However, when you compare that with laser cleaning, you don't use any secondary medium, so it's only light that is hitting the surface. It has very low environmental impact because, as you saw, the solid debris is removed on the spot by the vacuum pump. And another great advantage is the selectivity. So certain parameters such as pulse width, fluence, wavelength, and rep rate can be tuned to suit some material better than others. So in a sense that, for example, if you have different layers of paint of different colors on a metal surface, you can tune the fluence of the beam, which is energy per unit area, so that it would remove some of the paints and it would not remove some other color. So it would remove one color, it would not remove the other color. And I will show you in this video, which is a very useful one, different colors on a Coke Zero can. So red, white, and black. So let's see what happens. Okay, so this video actually has no sound, so you can see the laser beam is going over the surface and is removing the black paint. Although it will also cover the white and the red, it's not removing it. It's only removing the black. And this is really amazing, uh, you can say, advantage of laser cleaning. You cannot do that with sandblasting, for example. The reason for this is that the fluence has been tuned so that it is above the absorption coefficient of the black paint. So you can remove the black paint and below the absorption coefficient of the red and white, which have higher absorption coefficients. So so basically you need, or sorry, they have lower absorption coefficients. They need more energy. So the energy is below the threshold energy for the red and white. So that's why it's not removing it. It's only removing the black. So one question could arise, is it possible to tune it so that it removes the red and not the black? And the answer is no, because once you have the threshold energy above that of red, you automatically are above black. So, but you can do it so that you remove black and not red. So this is interesting application of laser cleaning selectivity. That shows the selectivity of laser cleaning. Okay, so next, next we want to talk a little bit about disadvantages of laser cleaning because no technique is perfect. So, uh, so laser cleaning is also not an exception, and there are some disadvantages. And one of the disadvantages of laser cleaning is the need for focusing. So, for a sandblaster, for example, you can see here the operator could stand at any distance. As long as you're within the vicinity of the wall, you could stand at any distance and do the job. But for laser cleaning, you need to be exactly at the focal length of the laser cleaner. So the lens has maybe 15 centimeter, 25 centimeter, 30 centimeter, 40 centimeter. You need to be exactly at that distance so that the laser cleaning works. You would hear the maximum sound when you are at that focal distance, and there will be maximum light emitted and maximum debris also, or fumes. So you would know that you're at the focal length. So that's one disadvantage. And the other thing is the lower speed. When you compare only the process speed between, let's say, laser cleaning and sandblasting, laser cleaning is slower as compared to sandblasting. So, in order to address some of these disadvantages, some of the accessories were designed. So one of them is the fume extractor nozzle that you can see on the left side. In this one, you can see that uh, there's this fume extractor nozzle has an opening on one side where the laser head or the lens could be placed, and then they have rollers on the other side. So as long as you roll these wheels on the surface you want to clean, this distance would be equal to the focal length of the lens, and you don't need to adjust your hand distance. So this will automatically clean, and then there's also a nozzle that removes the debris. So here you see our engineer on the right side is carrying the fume extractor, and also has a pump mounted on his back, so he's doing the cleaning and removing the debris. And the other accessory is robotic operation, which is quite useful because the robot could clean the surface, and basically the robot could hold the laser cleaner that could clean the surface at the focal point. And if you have operations that are very long, um, this would eliminate the fatigue factor for the operator. Or if you're in a radioactive environment where you don't want to be around the radioactive material too much, you can use the robotic to do the job for you. And here is one example that I'll show you in the YouTube video. So I'll activate this. Here is a metal pipe that is being cleaned of rust. And the robot is holding the 100-watt laser head, moving it around. Okay, so that was the robotic operation. Okay, next. We have some videos that compare sandblasting with the laser cleaning, and one of them is for ship sandblasting and also ship laser cleaning. So you can see here sandblasting operation. The operator is wearing a heavy protection equipment, personal protection equipment, and is cleaning the body of the ship and all the debris along with the sand, is going into the environment and contaminating the environment. So this is one, and then you would try the laser cleaning method. In this case, the operator is not wearing any personal protection equipment, only the goggles, and the vacuum tube is removing all the debris on site, and there's no contamination. Okay. All right, so now let's talk a little bit about the physics of laser ablation. Again, we are talking about the more general case of ablation. So, what are the important uh, parameters to consider? So, this is divided into the material properties and laser properties. So, for material properties, the parameters to be considered is optical attenuation coefficient alpha. So, for example, as you saw for the paint, alpha for black paint is larger than for the red paint, so it absorbs more, so it requires less energy to ablate. Then you have the thermal diffusivity, d tau in millimeters square per second, how easily it spreads, and the heat, how easily it spreads, and then the heat of vaporization in joules per gram. So these are three important material properties. And for laser properties, the fluence is very important, joules per centimeter square, the pulse duration, tau L, the wavelength, and the beam size. So I want to bring your attention to this diagram on the right side. So you can see that there's this orange beam that is falling on this surface, and it penetrates through the surface by uh, uh, depth of L alpha. This is called the optical penetration depth. And when the pulses are very short, that is less than 10 picosecond, this optical penetration depth is equal to the thermal penetration depth LT. So wherever the beam of light is penetrating, that's the same area where there is thermal penetration as well. However, when the pulse width is larger than 10 picosecond, the thermal penetration depth shown in yellow is larger than the optical penetration depth. And this thermal penetration depth is given by the equation here, the square root of thermal diffusivity multiplied by the uh, pulse duration. Okay, so you can see that now there is this uh, thermal penetration depth has some pulse width dependence. So it grows with pulse duration. So we also have to define the threshold fluence, FTH. So that is enough energy that needs to be deposited per unit area to ablate the material. So when the pulse width, sorry, is less than 10 picosecond, then the threshold fluence is just a product of the density, the heat of vaporization, and the optical penetration depth, and is just completely independent of uh, any of the laser parameters. But when the pulse duration is greater than 10 picosecond, the L alpha is replaced by L tau, the thermal penetration depth, which also has a dependence on the pulse width. So larger the pulse width, the larger will be the penetration depth, and the threshold fluence will also increase. So, so that is another degree of complexity that comes into picture where you have more or higher or larger pulse width. So it will vary with the pulse width, the threshold fluence would vary with the pulse width. Here is a comparison of uh, different zones, time zones. This is again for laser ablation in the case of cutting, in the case of drilling, sorry. So we are comparing the short pulses and long pulses. So for short pulses, like if you have some femtosecond pulses, you can see that everything is so neat and clean. So there's no debris, no melt zone, no micro cracks, no recast layer, no damage caused by adjacent structures, and the hole is very, very clean. But once you go to longer pulses, you have all kinds of liquid physics effects takes place. You can see surface debris, you can see ripples due to shock wave. You can um, basically see all kinds of new liquid physics effects taking place there and making it a little bit some ejected molten material. And this is not as clean as the one on the right side. So So this is not to say that do not use nanosecond pulses. All of our lasers have used nanosecond pulses. The only idea of showing this slide is that the heating effects are more pronounced in case of longer pulses as compared to, say, femtosecond pulses. So for picosecond, you have some liquid phase, some melting, and for nanosecond, you have liquid phase and some evaporation. Here's a comparison of the holes made by three lasers at different time zones. 200 femtosecond pulse, very clean. 80 picosecond, you can see there is some debris. At 3.3 nanosecond, you can see there is some melting. So femtosecond pulse is more suitable for machining, however, are usually low power and not suitable for paint removal. So here we want to compare the different surfaces. We talked about that earlier a little bit, but here are the actual graphs. So this absorption coefficient on the y-axis and the wavelength on the x-axis. So you can see that for metals such as steel and aluminum at larger wavelengths, basically mid-IR at 10 micron, the absorption coefficient is pretty small, so it doesn't absorb much at the mid IR wavelengths. But once you go to the near IR at 1 micron, the absorption coefficient increases. So this is the reason that when you have a steel surface and you have a near IR beam, you have more absorption on the surface. On the other hand, for plastics, ceramic, glass, and also paint, the near IR has very high absorption coefficient. The mid IR has a high absorption coefficient. The near IR has lower absorption coefficient. So these graphs need to be considered when you're choosing the laser. And now, another point is about different types of scanners. You have Galvo and Polygon scanners. So normally in most of our lasers, we use Galvo scanners that have two mirrors. One of them is stationary and the other one is rotating and generating a pattern. But the problem is that as the power increases, Galvo scanners become heavier and the scanning speed will go down. So if you're going to a higher and higher power lasers, there's another type of a scanner called the polygon scanner. So it has multi-facets and it rotates really, really fast. And this way it could tolerate higher energies also from higher power lasers. It's also a good combination with CW lasers. If you ever want to use a CW laser with a polygon scanner, it would work in some applications. So a polygon scanner is preferred to a Galvo scanner for higher power lasers. It also has other advantages such as they're lighter in weight, they are faster, for example, 50 meter per second compared to 10 meter per second. And affluent removal is also easier due to fast scanning speeds. All right, so Now we'll look at a few applications. Again, these are the ones that we haven't done ourselves, but I chose these just to demonstrate the capabilities of laser cleaning. And one of them, laser cleaning of aircraft parts. So you can see that the different robots are holding the lasers and cleaning different parts. So different parts of the aircraft. So one question is, why do you need to remove the paint from the aircraft? Because if you put additional layers of paint, the new paint on old paint, first of all, the quality won't be so good, and secondly, it will add to the weight of this aircraft. So for this reason, you need to remove the existing paint and then put a new layer on. So uh, you can use a CO2 laser, but you cannot use fiber optic when you do that, but you can also use the near IR laser, such as a neodymium YAG or fiber laser, and then you can use the flexibility of the fibers to do this cleaning. In any case, aircraft body is very sensitive, and you have to make sure that the substrate doesn't get damaged. So if you're using the near IR lasers, the parameters of the laser should be carefully chosen so that the substrate is not damaged. But it's definitely possible to do it using the near IR. Uh, Here's another very interesting application for nuclear decontamination. So here in Canada, in the provinces of Ontario and Quebec, we don't use coal. Uh, Quebec has a lot of water, so they use 94% hydroelectricity, but Ontario uses 60% um, nuclear power plants for generating electricity. So we rely heavily on nuclear power plants, the fission plants. So the problem is that within 30 to 40 years, there will be some cracks developed in the structure, and if you want to dismantle it, you have to dismantle it after 30 to 40 years. You can't just throw the parts out because they're all radioactively contaminated. So the concrete walls need to be cleaned, and also the metals that are inside the plants, the tools, the pipes, they need to be cleaned and then recycled for the next generation power plants. So the mechanism is that corrosion of the metal pipes basically throws different uh, particles of metal into the reactor coolant, and they'll go into the active area of the reactor, get radioactive, and they come back and they deposit on the metals in the form of oxides. So these oxides, which are mostly which mostly contain cobalt 60 with a half-life of 7 years, need to be cleaned from the pipes. And this uses the process of spallation that I talked about earlier. So the near IR beams, they are uh, transparent. The oxides are transparent to the near IR beam. So if you want to clean it with the laser cleaner, it will heat the metal underneath, and then that will generate a shock wave and blast the metal surfaces. So this is a very useful method of cleaning pipes, contaminated pipes in reactors that need to be uh, basically need to be cleaned or decommissioned. So let's talk a little bit about our systems. We have several laser systems. The 100 watt, which is our original unit, I showed you this earlier, is shown in here. Variable rep rate and pulse width, a fiber length of 5 meters. Then we have the 200-watt unit on the right side. This is a little bit narrower and has some cabinets where you can store goggles and lenses. Uh, so this was the second unit that was built and was used for some bridges. And our second generation 100-watt unit is shown here. And this was definitely necessary because, especially for ship cleaning, you need to go through the hatches sometimes, and one man needs to carry that like a suitcase. So, for some applications, there's not enough space to carry a bigger laser machine. So this is very suitable for portability of the instrument. It's 60% smaller and 40% lighter than the original design. And there was an iPad. If you look at the 100 watt, you can see there's an iPad on the box where you can do all your parameter selections. And this iPad is now replaced by a user-friendly touch encoder that you can see here. So this will take less time, less space. So these are some safety features. You can also put airline here to clean the lens with the air. Status light, safety accessory, and this is also on the right side another possible design where it's actually like a torch. So the beam and the body of the laser head are parallel to each other, so it could be easier to insert that into certain tight areas in a ship, for example. Then we have the 300 watt system that has been recently completed. Yeah, we have sold 2 units, and you would be interested to know that one unit was sold to a company that makes fences for cattle industry, and the other was sold to another company that is in construction. So this 300 watt unit, you can see two views of it. It's been recently completed and is available. Here are some of the parameters of this. And then we also have the 500 watt unit, which is the most powerful laser cleaner. You can coil the fiber optic on top and put this lid on top of it to protect it. Uh, the rep rate of 2 to 50 kilohertz, and it comes with the fiber optic cord of 11 meter or 22 meter beam delivery fiber cable. It also has a chiller because there's enough heat to produce that a chiller is required to cool different parts. So let's go into some of the case studies quickly. These are case studies where we have done the work. This is not just an application from a paper or a presentation. This is we have actually done these case studies. So the first one was testing at the Perma-Fix nuclear decontamination facility in Richland, Washington. So this facility takes care of low level and intermediate level uh, radioactive contamination and cleans them. Uh, so quite famous in the US. So we took the 100 watt unit back in 2017 to their facility, and they set up a negative pressure area where you can see the engineers and their technicians are in heavy personal protection equipment. They are inside the negative pressure area, and the actual box was kept outside of that. And our engineer was right near the box and basically controlling things. So several objects were cleaned. You can see concrete ecology block, metal jackhammer, metal C clamp, brass cutting torch, steel plate, and so on. And a level was defined as the clean level. It was 1,000 disintegration per minute. So some objects took longer passes to do that. So you can see, for example, the concrete took 4 passes, and the rate their contamination decreased to below 1,000. Some others they took only 1 or 2 passes, like the metal jackhammer. So let's look at the video here. Maybe we don't have time to show all of it, but we'll show some of it so you can take a look.
Why should you use Miro? Well, when you draw on a whiteboard, no one sees it. With Miro, you plan together in.
So 100 watt system. So here the metal is being cleaned, the metal plate, the The engineer technician is cleaning it with our laser cleaner 100-watt system, and the radiation technician is measuring the disintegration per minute. And this tube goes to the vacuum pump through the HEPA filter, so collects all the debris. You can see that the laser head is all wrapped in plastic bags so that it doesn't get contaminated. To less than 1,000. Initially, it was 5 with laser. It went down to less than 1,000. Initially, it was 5,000. Of the C clamp is being cleaned. There is a curvature there. After 2 passes, it was 4,000. And finally, there is a concrete block, which was the most difficult one. That's why it has a small beam because there's kinds of pore structure. So there has all kinds of pores. Okay, so that was the Permafix trip. All right, next one. The next case study is what we did last December in McMaster University in Hamilton, Ontario, where they have a radiation facility. They have a hot cell. You can see it here. There are two mechanical arms there, uh, right here. And there is a hot cell in here. So they generated using their particle accelerator, the fluorine 18, which is a short half life radioactive isotope. His half-life is only 109 minutes. The reason this isotope was chosen was if there was a mistake during the operation and a mess was made, you just had to wait for about 24 hours for all of the radioactive material to decay. So there was no need for any worry. So for safety reasons, this was chosen, and this material was dissolved in methanol solution, and using a paintbrush it was applied to several surfaces, several metal surfaces. So, for example, you can see these are the surfaces that were used. There was brass, steel, stainless steel, aluminum, and chrome vanadium. So the laser cleaner was mounted on a cobot, which is a collaborative robot, and some alignment had to be done. And this was programmed to move around and basically clean the contamination from the surface. So one would do a wipe first and measure with the Ludlum detector what the radiation level is. And then afterwards, a few scans were done. You would measure again to make sure that the radiation level fell below a certain threshold level, which we define as 500 CPM. So here's a video that shows you what happened there. I'll show you this video. So the brass is shown here. This is the brass. So you see at some point that the operator is measuring the contamination level from this surface, and at some point the laser cleaner would come on and would clean the surface. This is all mounted on the robot, on the cobot, and it would do several scans back and forth. And then at the end, there will be another measure just to make sure that the radiation falls below 500 CPM. This was presented at WM 2022 in Phoenix, Arizona, and we had a poster that presented this work. These are some of the parameters. So for softer metals such as brass and aluminum, less number of scans were required, and normally something like 200 nanosecond was used. But for harder materials such as steel, chrome, vanadium, the setting was 350 nanosecond. And there were more passes, up to 15 passes were required to remove the contamination. We also have some trials in the shipping shipyard in Halifax. We took the 500, the 200, and 100-watt lasers up there and cleaned different areas of the ship. Here you can see the ship is being wrapped in tarp because they were planning to do sandblasting, so they were protecting the environment from the mess that it would make. And both cleaning was done both offshore and onshore. So here is, for example, uh, onshore cleaning that was done in Shelburne ship repair. This is offshore with the 500-watt laser. There was a 15-meter fiber cable that was taken inside the plenum, and some paint was removed. Also, a 4 mil average profile was made successfully for the uh, bilge area, which is down at the bottom of the ship. The 100-watt laser was taken down, and some cleaning was done. And the 200-watt was done for onshore cleaning in Halifax shipyard for removing rust and paint from different surfaces. So in general, the operation was quite useful, but we had some feedback that the managers of the facility thought that we should reduce the size of the laser head and the laser controller, which led to the basically production of the 100-watt Gen 2 that I showed you before. The 100-watt Gen 2 model is right here, and this is now ready and uh, suitable for doing the ship cleaning in the bilge. Okay. Some other case studies, not going into detail due to shortage of time. Uh, the leaded paint laser cleaning, has to be very careful about lead because it's very bad for the health. And for this reason, not only a HEPA filter need to be used, you also need to use a BOFA filter that has uses these scroll plates in a circular geometry, and the particles, the heavier particles, they go inside, and due to centripetal force they get filtered out because they go into larger and larger circles, and they fall into these scroll plates, and then the rest would go into the HEPA filter. So you need more precaution for leaded paint. Another application in Canada Aviation Museum. Sorry, this is a case study. Canadian Aviation Museum removing soot and oil from different engine parts. Uh, Very useful for this application. And this one I want to show, this is the polygon scanner. So I'm going to show this video. So this is actually a prototype polygon scanner. This is not the one that we are using in the laser system. This is an inexpensive polygon scanner, and you can see that the different facets are not aligned. That's why you see there are 8 lines in here. So these are not happening simultaneously, but because they're so fast that the camera could not distinguish that this is happening one at a time. So here, let me try again. So in our laser cleaner, the 300-watt system, we use a polygon scanner, and all the facets are aligned, so there will be only one line, not 8 lines. So this is very useful for faster scanning speeds, and it could also tolerate higher powers. Okay, next one. We also have the NDT inspection system, which uses a capacitive 2D imaging and impedance spectroscopy to determine where is the location of the rust. And before the actual laser cleaning operation, we would examine the location of the rust using the non-destructive testing. Uh, and final slide is about laser cleaning in the greasy and bacteria infected surfaces. In the food industry, you have these greasy barbecue plates that need to be cleaned, and near IR laser could be used to blast these microfilms that are very sticky, as you can see on the right side. And for bacteria cleaning, this is application, not a case study. So we didn't do it, but I dug out the information from a paper. They have compared different types of laser, neodymium YAG laser, and CO2 laser. Were able to very effectively remove these biofilms that were sticky. And basically, these are more effective than detergent solutions for removing bacteria. So with this, we come to the end of our presentation. In conclusion, we showed that laser cleaning is a very environmentally friendly, reduces damage to the substrate, has a great selectivity, doesn't require secondary medium, reduces health hazards to operator, is less noisy, more economical as compared to the other methods. We saw the different parameters of the lasers and material properties, how they affect the performance of laser cleaning. We compared polygon and galvo scanners. We also showed the difference between CO2 laser and near IR lasers, and basically showed that you could use near IR laser equally well if you choose the parameters correctly. And laser cleaning could be a very good replacement for sandblasting in shipping industry, as our trial in Halifax shipyard showed that. And finally, robotic laser cleaning was used to clean F-18 radioactive isotope from the surfaces of different types of metals, and the operation was very successful. The results were presented in WM 2022 conference in Phoenix, Arizona. So this brings us to the end of our talk. Uh, Thank you for your attention, and we will send a feedback form to you. If you could please fill out this feedback form. If you have any comments, any suggestions to improve the webinar, we will definitely consider that. So at this point, I would ask anyone who may have a question to, you can ask your question. All right. So if there are no questions, I thank everyone for their attention and wish you a pleasant evening. Thank you. Bye.